Welcome to Section 7, Lesson 7. In the previous two lessons, we covered polynomial long division and synthetic division. Today, we build the theoretical foundation underneath both algorithms with two beautiful and useful theorems, the remainder theorem and the factor theorem. The remainder theorem says that when a polynomial p of x is divided by the linear factor x minus c, the remainder of the division equals exactly p of c, the value of the polynomial evaluated at c. The factor theorem says that x minus c is a factor of p of x if and only if p of c equals 0. Both theorems make synthetic division a powerful tool for polynomial evaluation and for testing whether a candidate is a root of the polynomial. Today we lock in both theorems, prove them from the division algorithm, and apply them to evaluation and root finding problems. First idea on the board, the remainder theorem statement and proof. When polynomial p of x is divided by the linear divisor x minus c, the division algorithm gives p of x equals quotient times the quantity x minus c plus remainder. Substitute equals c into both sides. P of c equals quotient evaluated at c times the quantity c minus c plus remainder, which simplifies to p of c equals quotient at c times 0 plus remainder, which simplifies further to p of c equals remainder. The remainder is therefore exactly p of c, the value of the polynomial at c. The remainder theorem connects polynomial evaluation to polynomial division directly. Second idea, the factor theorem statement and proof. The factor theorem states that x minus c is a factor of p of x if and only if p of c equals 0. The proof uses the remainder theorem in both directions. If x minus c is a factor of p of x, then the division of p by x minus c has remainder 0 by definition of factor. By the remainder theorem, the remainder equals p of c, so p of c equals 0. Conversely, if p of c equals 0, then by the remainder theorem the remainder of dividing p by x minus c is 0, which means x minus c divides p exactly, which means x minus c is a factor. The two-way implication is the factor theorem. Practical applications. The remainder theorem makes synthetic division a fast polynomial evaluation tool. To evaluate p of c, set up the synthetic division tableau with c at the left and the coefficients of p across the top, run the algorithm, and the bottom right entry is p of c. This is dramatically faster than direct substitution for high-degree polynomials. The factor theorem makes synthetic division a fast root testing tool. To test whether c is a root of p, run synthetic division by x minus c and check whether the remainder is 0. If yes, c is a root and x minus c is a factor. If no, c is not a root. Combined evaluation and root testing capabilities make synthetic division one of the most widely used tools in algebra and beyond. Two theorems that together make synthetic division a powerhouse tool for polynomial evaluation and root finding. Both follow from the division algorithm dividend equals quotient times divisor plus remainder applied to the linear divisor x minus c. When polynomial p of x is divided by x minus c, the remainder of the division equals p of c, the value of the polynomial at c. The proof by the division algorithm, p of x equals q of x times the quantity x minus c plus r, where r is the constant remainder. Substitute as c p of c equals q times 0 plus r equals r, so r equals p of c, exactly as claimed. The expression x minus c is a factor of p of x if and only if p of c equals 0. The proof has two directions. Forward, if x minus c is a factor of p, then dividing gives remainder 0, which by the remainder theorem equals p of c, so p of c equals 0. Backward, if p of c equals 0, then by the remainder theorem the remainder of dividing p by x minus c is 0, so x minus c divides p exactly, which means x minus c is a factor. The two-way implication is the factor theorem. Practical use 1. Fast polynomial evaluation. To compute p of c for a polynomial of degree n, instead of substituting c into the polynomial directly, which takes order n squared multiplications by Horner's naive method, use synthetic division by x minus c. The bottom right entry of the tableau is p of c. The synthetic division evaluation takes only n multiplications and n additions, which is the optimal evaluation algorithm for polynomials and is in fact equivalent to Horner's rule. Practical use 2 fast root testing. To test whether C is a root of P, run synthetic division by x minus C. If the remainder is 0, C is a root and x minus C is a factor of P. The quotient polynomial in the tableau is P divided by x minus C with degree 1 less than P. If the remainder is non-zero, C is not a root and x minus C is not a factor. Combined synthetic division root testing is the foundation of the rational root theorem in Lesson 9, where rational candidates are tested one by one until all roots are found. Here is the first worked example. Use the remainder theorem and synthetic division to evaluate p of x equals 2x cubed minus 5x squared plus 3x minus 7 at c equals 4. We will compute p of 4 directly by substitution and then by synthetic division and compare the results. Step 1. Direct substitution. Plug x equals 4 into p of x. Compute term by term. 2 times 4 cubed equals 2 times 64 equals 128. 5 times 4 squared equals 5 times 16 equals 80, with a negative sign making it negative 80. 3 times 4 equals 12, constant negative 7, sum 128 minus 80 plus 12 minus 7 equals 53. So p of 4 equals 53 by direct substitution. Step 2. Synthetic division setup. Coefficients of p are 2, negative 5, 3, negative 7. Write 4 at the left of the tableau, separated by a vertical bar. Write the coefficients across the top. Step 3. Run the synthetic algorithm. Bring down 2. Multiply 2 times 4 equals 8. Add negative 5 plus 8 equals 3. Multiply 3 times 4 equals 12. Add 3 plus 12 equals 15. Multiply 15 times 4 equals 60. Add negative 7 plus 60 equals 53. The bottom right entry is 53. Step 4. Compare results. Direct substitution gave 53, synthetic division gave 53. The two answers match. By the remainder theorem, the synthetic division remainder always equals p of c, so the match is guaranteed for any polynomial. Synthetic division evaluation is faster than direct substitution for high-degree polynomials because each step is a single multiplication and addition with no exponentiation overhead. Step note. The synthetic division evaluation is mathematically equivalent to Horner's rule, which rewrites the polynomial as a nested sequence of multiplications and additions. The polynomial 2x cubed minus 5x squared plus 3x minus 7 rewrites in Horner form as the quantity 2x minus 5 times x plus 3 times x minus 7. Substituting x equals 4 into the Horner form gives the same arithmetic that synthetic division produces in the tableau, step by step. So p of 4 equals 53 computed two ways, with synthetic division providing the faster method via the remainder theorem. The big lesson from this example is that synthetic division is not just a division shortcut, it is also a polynomial evaluation shortcut. The remainder theorem makes the equivalence the remainder is p of c. Use synthetic division for any polynomial evaluation task on polynomials of moderate or high degree. Here is a second worked example. Use the factor theorem to test which of c equals 1, 2, or negative 3 is a root of p of x equals x cubed minus 4x squared plus x plus 6. For each candidate, run synthetic division and check whether the remainder is 0. Test c equals 1, synthetic divide by x minus 1, coefficients 1, negative 4, 1, 6. Tableau bring down 1. Multiply 1 times 1 equals 1. Add negative 4 plus 1 equals negative 3. Multiply negative 3 times 1 equals negative 3. Add 1 plus negative 3 equals negative 2. Multiply negative 2 times 1 equals negative 2. Add 6 plus negative 2 equals 4. Remainder is 4, not 0, so c equals 1 is now a root, and x minus 1 is not a factor. Test c equals 2. Synthetic divide by x minus 2. Tableau bring down 1. Multiply 1 times 2 equals 2. Add negative 4 plus 2 equals negative 2. multiply -2 times 2 equals -4. Add 1 plus -4 equals -3. Multiply -3 times 2 equals -6. Add 6 plus -6 equals 0. Remainder is 0, so c equals 2 is a root and x minus 2 is a factor of p of x. Test c equals -3. Synthetic, divide by x minus -3, which is x plus 3, with c equals -3. Tableau, bring down 1. Multiply 1 times -3 equals -3. Add -4 plus -3 equals -7. Multiply -7 times -3 equals +21. Add 1 plus 21 equals 22. Multiply 22 times -3 equals -66. Add 6 plus -66 equals -60. Remainder is -60, not 0, so c equals -3 is not a root. Step 4. Reduce using the found root. Since c equals 2 is a root, we can extract the factor x minus 2 and reduce p. The quotient from the synthetic division tableau in step 2 has coefficients 1, -2, -3, giving the quotient polynomial x squared minus 2 minus 3. So p of x factors as the quantity x minus 2 times the quantity x squared minus 2x minus 3. Step 5. Find remaining roots. Factor the quotient further, x squared minus 2x minus 3 factors as the quantity x minus 3 times the quantity x plus 1. So the full factorization of p of x is the quantity x minus 2 times the quantity x minus 3 times the quantity x plus 1. Roots of p are x equals 2, 3, and -1. 3 rational roots total. So the roots of p of x are 2, 3, and -1, found by testing candidates with the factor theorem and reducing via synthetic division. The big lesson from this example is that the factor theorem combined with synthetic division provides a systematic algorithm for finding rational roots of polynomials. Test each candidate on a hit, divide it out to reduce the polynomial, repeat. The rational root theorem in lesson 9 narrows the candidate list, and this example previews how the testing and reducing workflow operates in practice. 3 mistakes that catch every algebra student during their first weeks of remainder and factor theorem work. Each one is fixable with a small explicit habit applied on every problem from now on consistently. First mistake: getting the direction of the remainder theorem wrong. A student writes that the remainder equals p of x divided by x minus c, somehow treating the entire division as the result. The correct statement is that the remainder of the division of p of x by x minus c equals p of c, the value of p at c. The reason is the substitution argument. Setting x equals c kills the divisor term in p of x equals quotient times divisor plus remainder, leaving p of c equals remainder. Always remember the substitution: plug x equals c into the division identity, and the divisor vanishes. Second mistake: getting the sign of c wrong when extracting from the divisor. A student looks at the divisor x plus 5 and uses c equals plus 5 in the synthetic division tableau and the remainder theorem evaluation, when actually c equals -5 because the divisor must be in the form x minus c. Plus 5 would be correct only if the divisor were x minus 5. The fix is to always rewrite the divisor explicitly in x minus c form before extracting c. The sign flip is critical and corrupts every downstream calculation if missed. Third mistake: forgetting the if and only if structure of the factor theorem. A student knows that if x minus c is a factor, then p of c is 0, but does not remember the converse: if p of c is 0, then x minus c is a factor. Both directions are part of the theorem, and the converse is what makes the theorem useful as a root testing tool. The fix is to internalize the two-way nature. The statement p of c equals 0 and the statement x minus c divides p of x are exactly equivalent, with each implying the other. The remainder and factor theorems show up across polynomial evaluation, root finding, numerical analysis, and computer graphics continuously. 4 broad sectors below where every working professional applies these theorems routinely. In polynomial evaluation, Horner's rule is the standard fast method for computing P of C, and it is mathematically equivalent to running synthetic division and reading off the bottom right entry as the remainder, which by the remainder theorem equals P of C. Horner's rule appears in every numerical computing library, every embedded device that evaluates polynomials, and every educational setting where polynomial evaluation matters. The remainder theorem is the conceptual justification for why Horner's rule produces the correct value. In algebraic root finding, the factor theorem combined with synthetic division provides the standard algorithm for finding rational roots of polynomials with integer coefficients. The rational root theorem in Lesson 9 narrows the candidate list to a finite set, and each candidate is tested by synthetic division checking for zero remainder. Hits become factors that are extracted via the same synthetic division pass, misses are eliminated. The combined algorithm efficiently finds all rational roots and reduces the polynomial to a quotient of lower degree. In numerical analysis, polynomial root finding algorithms like Newton's method, the Bairstow method, and the Jenkins-Traub algorithm all build on top of Horner-style polynomial evaluation. Computing the polynomial value and the polynomial derivative at the current iterations estimate uses synthetic division for both. Modern numerical software libraries implement these algorithms with the same fundamental polynomial evaluation primitive that the remainder theorem describes. In computer graphics and computer-aided design, Bezier curves and B-splines are evaluated using Horner-like nested multiplication for performance. Every smooth curve drawn in graphics software, every smooth animation interpolation, every smooth surface in three-dimensional modeling uses polynomial evaluation as its inner loop primitive, and the remainder theorem-based evaluation is the standard fast method employed in production graphics engines. 3 things to take with you from this lesson today. The remainder theorem and factor theorem make synthetic division a powerhouse tool for polynomial evaluation and root finding, and they connect polynomial division directly to polynomial values and polynomial roots. Today's theorems are the conceptual foundation underneath the rational root theorem and finding all roots techniques in the next lessons. First, the remainder theorem says that when polynomial p of x is divided by the linear divisor x minus c, the remainder of the division equals exactly p of c, the value of the polynomial at c. The proof comes from substituting x equals c into the division identity p of x equals quotient times divisor plus remainder, which kills the divisor term and leaves p of c equals remainder. The remainder theorem makes synthetic division a fast polynomial evaluation tool. Second, the factor theorem says that x minus c is a factor of p of x if and only if p of c equals 0. The if and only if structure is essential. Both directions are part of the theorem, and the converse is what makes the theorem useful as a root testing tool. Forward factor implies 0, remainder implies p of c equals 0, backward p of c equals 0 implies 0, remainder implies factor. Third, practical use. Synthetic division by x minus c does double duty. It evaluates p of c via the remainder theorem, and it tests whether c is a root via the factor theorem, both in a single pass through the tableau. If the remainder is 0, c is a root, x minus c is a factor, and the quotient polynomial in the tableau gives p divided by x minus c with degree 1 less. This combined capability is the foundation of the rational root finding algorithm coming up in Lesson 9. Coming up next, the lesson called Graphing Polynomials, which uses the structural information about polynomials to sketch their graphs efficiently. End behavior, x and y intercepts, and turning points each follow from polynomial structure, and the lesson teaches how to combine them into accurate graph sketches without point-by-point plotting.